Hello? Oh, there we go. So today we have special guests from IBM, and they're going to be talking about the POWER Hypervisor. And right now we have David Larson, who will be speaking about, well, features and designs of the IBM POWER Hypervisor. And a little intro about him is he got his bachelor's degree from North Dakota State, right? Yeah. And he's worked a lot with i5OS PACE, which is an AIX runtime environment for i5OS. So yeah, I'll just turn it over to him, and yeah.
Can everyone hear me fine? How about now? Better? Is that any better? Okay. So just give you a quick overview of what we're going to go through today. We're going to have three major topics. What? Oh. Let me see if I can get this done. Okay, how's that? Okay, just give me this one.
What number is that?
This is, do you want to do wireless?
Yeah, what numbers? What else? One.
How's this? Okay, is that better? Yeah, we'll just use hand on. As you can tell, we're programmers. We don't do this very often. So we're going to basically have three major sections of this discussion. We're going to start out by talking about the features of the pSeries POWER Hypervisor. For those who aren't familiar with what I and pSeries are, they're basically the same thing. It's just a branding and marketing distinction. pSeries, the servers that primarily run the AIX operating system, and iSeries, the ones that are primarily focused towards i5OS customers. We're going to talk a little bit about in-depth the virtualization features of how we do memory and processors and virtual I/O devices. And then I'm going to turn it over to Greg, and he's going to talk about our platform I/O subsystem design. It's a little bit more complex than your standard PC, so he's going to cover some of that. Before we get started here, I'd just kind of like to give a brief history of how we got to where we are today. Originally, back in the mid-90s, the iSeries brand came out with a feature for their operating system called LPAR, logical partitioning. And that was basically the first hypervisor that we had in the POWER architecture. It was actually packaged as part of the operating system. And the way that worked is you would install your operating system. That would be what was called your primary partition. And then you would use that primary partition to create and configure secondary partitions. And then the primary partition was kind of the control point for that. Then later on, about the time of the POWER 4 processor, the pSeries brand came out with their own hypervisor that was different. They took a different packaging structure. They were actually packaged as part of system firmware, so they weren't part of the operating system. And then they also had a different control point. Rather than using an operating system to configure the partitions, what they actually did was have an external PC with some specialized software installed on it that they call the Hardware Management Console, or HMC. And then that connected up externally through a serial port to the server. Then when POWER 5 came around, that's when we got to the POWER Hypervisor. And it was basically the merging of those two different hypervisors. We adapted the pSeries packaging structure and management structure, and then the code base was actually based off the original iSeries hypervisor code base. So what exactly is the hypervisor? It's basically the lowest layer of firmware that sits right on top of the host processors and is in charge of IPLing the system, initializing all the hardware devices, and then providing virtualization services to basically split the processors, memory, and I/O devices up into separate logical partitions. And then each logical partition will run its own unique instance of an operating system. And then in addition to just virtualizing and partitioning the actual physical resources of the hardware, it can actually create pure virtual devices. Some examples of that would be consoles for the partitions. We support up to 254 consoles no one wants 254 serial cables coming out the back of their box. So instead what we do is provide virtual serial devices that are very similar to real ones. They have transmit and receive buffers that send and receive characters, and then that goes out through the HMC where there's a virtual console application that can connect to those. And then we also do things such as virtual LAN devices. So that if you have multiple partitions that want to communicate back and forth, you don't need to have 2 LAN cards with the cable connecting them. You can just have it completely internal. And then there's also some higher level functions such as error reporting, management features, etc. that are part of the hypervisor. We had several goals when we actually created this thing. The initial motivation was actually more of a server consolidation thing, where we had customers that had several smaller boxes. They were getting old, going off for hardware support. It was hard to sell them a bigger box because they didn't need that much CPU capacity because their computing needs hadn't increased. But by doing logical partitioning, we could give them one big box, and they could take all their smaller servers, put them on that single box, and be happy. And it would also played into places once Linux started becoming popular where you had multiple different workloads that demanded different operating systems. For example, there's some customers that have multiple stores throughout the nation, and they had a Linux application and an AIX application that they wanted to run at every site. Well, by creating 2 partitions, one for Linux and one for AIX or i5OS, they can get away with just 1 server at each store instead of multiple servers. Another goal that we had was to do robust isolation between these partitions. The common analogy we used is we wanted something called air gap security, where basically we want 2 separate partitions running on the same server to be secure and isolated from each other, just like they were on 2 separate boxes that were physically separated, that didn't have a connection between them. Along with that, it kind of plays into the next point here, is that we provide services to dynamically reconfigure the system on the fly. No one really wants to reboot their box just to move a processor between partition A and partition B, or to move an I/O device, such as a tape drive or something. And to do that securely, we have to make sure that we're very careful when we move those devices. For example, when we move memory between partitions, prior to actually letting partition A give up that memory, we ensure that there's no way it can touch that memory anymore. And then after we've done that, we actually go throughout and zero that memory out so that there's no residual data left from partition B, or from partition A once it goes to partition B. And then we also do a similar thing when we're moving physical I/O devices. Whenever a PCI adapter moves from partition A to partition B, we'll actually go out and power cycle that adapter in the middle so that there's no residual state left in any of the registers in that device. And then we also provide both out-of-band and in-band management interfaces. Today, the primary out-of-band interface is the HMC, and then in-band is a product we called have Integrated Virtualization Manager. It's basically an appliance partition. It's a specialized version of AIX that you install it, and then you point a web browser at it, and you can use it to create and configure the rest of your partitions. And some people may wonder, well, why do you need multiple ways to manage the system? And that kind of comes into play because we ship this firmware on wide ranges of systems. The same hypervisor runs on your little 2 CPU blade server that plugs into a Blake Center, all the way up to a 64-way high-end server that's about the size of a refrigerator. People don't want to buy an external PC to manage their blade. It doesn't make any sense. But on the high end, you also need that external management entity to control things like frame assignment and power control and stuff like that. I'm going to talk a little bit here about our approach to virtualization. It's a little bit different than what you see in the PC era. In the PC area, typically you've got something like VMware or Zen or Microsoft's Virtual PC, where it takes unmodified operating systems and makes what's underneath it look like a new PC. So those operating systems run without changes. The approach we've taken is a little bit different. We do what's called Paravirtualization, where we actually do require changes to the operating system. It's intimately aware that it's running on top of a hypervisor, and it has to use the hypervisor services to access certain hardware resources that it couldn't normally access otherwise. And to do that, what we did is we provided an interface called hypervisor calls. Anyone who's familiar with kernel architecture knows that applications make system calls to request services from the operating system. Hypervisor calls are the exact same thing for an operating system. It's just a special instruction that it uses to call into a well-defined API. And then to give you an example of what we kind of use that for hardware page table. That's basically our translation mechanism. The operating systems aren't allowed direct access to that because they could create mappings to other partitions of memory. So instead, they have to use a well-defined set of APIs to do things such as insert mappings, delete mappings, change page protections, etc. And then those same interfaces are also used to implement pure virtual devices. And it's kind of nice the way we've done the pure virtual devices at that layer is that we can make them look like real physical devices. Our virtual I/O architecture has the concept of there's a virtual bus, and you plug virtual adapters into that virtual bus. And for most of the device driving program model, it looks exactly like a real device. Take interrupts, for example. The way that it uses to accept an interrupt and acknowledge the interrupt, change priority, it's the exact same interfaces that a real I/O device uses. And then if anyone's interested, there's actually, if you go out to the power.org website, all of the hypervisor calls that are part of our hypervisor are documented as part of what we call the PAPR, the Power Architecture Platform Requirements. And I think you can go out there and register as a developer and download that for free and take a look if you care to. And then beyond the basic partitioning features, we also provide some advanced features. I'm just going to cover a couple of those real quick. Capacity upgrade on demand. We have some models of servers that we actually ship CPUs and memory in that aren't activated or licensed, so the customer can't use them. And then when the customer has two options, we do what's called permanent upgrades, where they can call in and get a secure activation code that permanently licenses those processors. And then we also have features called reserve and utility capacity on demand, where basically the customer can rent the use of those processors for a short period of time. A good example of that would be, let's say you have a business that has a web presence and they have a peak demand during the holidays and they don't want to incur the expense of having those processors licensed throughout the entire year. For their peak sales days, they could take and license additional processors for just a couple hours or a couple days or a couple weeks. Partition mobility, this is actually something that we're going to cover in the workshop that we're doing after this presentation. That's the ability to take a partition on system A and transparently migrate it over to system B while it's running. That'll be pretty interesting. And then we also have some advanced processor and I/O recovery features. The I/O recovery has been there for quite a while. That basically consists of isolation, so if you have a PCI adapter that's causing parity errors or going bonkers or starting to fail, any ill effects of that are basically contained to whatever partition owns it, and also contained to just that slot, so it doesn't mess up the rest of the PCI bus. And then the processor error recovery is something that's fairly new that was added in Power 6. There's two portions of that. There's a thing called instruction retry recovery. What that basically is the processor periodically checkpoints its state, and then if it encounters an error, what it will do is it will back up to that checkpoint and retry whatever operation it was doing. Hopefully it succeeds, but if it doesn't succeed, prior to Power 6, what would happen is the whole system would crash. In Power 6, we just basically check stop that single CPU. And then we can go on from another CPU that's still functioning on the system, extract that checkpointed state, do some checks to make sure it's valid, and then if there's spare CPUs in the system, insert that state into a spare CPU, and the partition continues to run and doesn't even know that anything ever happened under the covers. And then we also do power management. It mentions I/O power management here. That's something we've had for a long time. Basically, when the system's idle or you have partitions that are powered off, we go find all of the PCI devices that they owned and turn them off so they aren't consuming power when they're not being used. And then we also added some CPU power management features in Power 6, where when the processor's idle, we'll put it into a low-power nap state that cuts off clocks to a good portion of the processor core. And then I don't have it listed here, but there's another thing I thought about when I was reviewing this. Another nice feature we have is concurrent firmware update. We have a couple releases of firmware a year, and then we have several service packs to do fixes to those releases. And when we do a service pack to put fixes out for release, we don't require the customer to reboot their system to apply that. We've developed a set of tools and technologies that we can basically examine what code did they change to make the fix, package just those changes up into a binary, and then modify the existing firmware that's running on the system to use that new code without forcing a reboot. So here's just kind of a picture to give you a better idea of what our firmware structure looks like. What's actually referred to as the Power Hypervisor is a combination of this hidden service partition and the actual hypervisor code down here. What the hidden service partition is it's basically a little miniature operating system that does a lot of the higher level functions, such as creating partitions, deleting partitions, doing error reporting. It's just much easier to do that sort of function up where you can create tasks and processes instead of a very restricted kind of BIOS-like programming environment, which is what the hypervisor is. And then in this example, we've got 4 partitions. In each partition, there's a little bit of partition firmware that sits on top of the hypervisor. If anyone's familiar with what open firmware is, that's basically partition firmware. And then we've got 4 partitions, 2 Linux ones, an i5OS, and an AIX. This is just kind of another picture here that kind of shows you what hardware we do focus on for virtualization. For processors, there's 2 ways you can do that. You can either just split up the processors into and processor boundaries, which is what we call dedicated partitions, and that would be where you assign a whole processor to a partition, or we can do micro partitions, which is essentially shared processors where you have multiple partitions that use the same physical CPU. Memory is fairly basic. What we do is there's a user-defined granularity level. It ranges from 16 to 256 gigabytes, or sorry, 256 megabytes, and then they can assign it in that increment to different partitions. And then for PCIe I/O devices, the hypervisor itself, what it does is it just partitions at a slot level. So we take adapter A and assign it to partition A, and adapter B and assign it to partition B. And then we ensure that there's no way that adapter A and B can talk to each other, or that partition A could access partition B's adapter. And then there's also something called Virtual I/O server that it's at a higher level. It's actually kind of like a specialized appliance partition. It can take a single physical adapter and then split it up into services that are provided to multiple partitions. Now we're going to kind of go into some specifics of how we actually do some of the virtualization. For processors, basically what we have is the concept of a virtual processor. And what you do is you assign those virtual processors to a partition. So when the customer is sitting there creating their partition saying, I want this box to have 2 CPUs, he doesn't really choose 2 specific CPUs in the box. Instead, what he does is assign it 2 virtual processors, and then we find physical CPUs to back those virtual processors. In the case of micropartitions, what it actually is there's a pool of physical processors that make up a shared processing pool, and then all of the partitions run on top of that shared processor pool. So in this picture here, you can see that we've got some dedicated partitions on the left, 2 one-way partitions, 1 two-way partition, and then on the right you've got micropartitions where there's 4 physical CPUs, capacity in the pool, and then there's a total of, looks like about 7 virtual processors that are all being time sliced on those physical CPUs. So what is a virtual processor? It's basically just an encapsulation of the state that the operating system can see. And for the power processor, that includes all of the threads on a CPU core. Currently, we have processors that have 2 cores per chip, and then each core actually has 2 distinct threads of execution. And those 2 threads of execution always remain within the same partition. We don't have the capability to say thread 0 runs in partition A and thread 1 runs in partition B. So that includes all the things like the floating point registers, special purpose registers, general purposes registers, interrupt state, translation context that's thread specific. We have a thing called a segment look-aside buffer in our architecture that's thread specific. And this is used by both shared processor partitions and dedicated processor partitions. The primary difference is that shared processor partitions, there's a bunch of additional data hung off to this that's used for managing entitlement and time accounting. And the nice thing about this is, when I gave you that example like processor error recovery, when we extract the state from a failed processor, what we basically do is shove it into a virtual processor and then just plop it onto a different processor. And it's really nice. We don't have special code pass for it or anything. When you get to micro partitions, there's some optimizations that we had to take and implement. The example here, just to kind of explain the picture, you've got 2 virtual processors, 0 and 1. Each one's got 2 threads, 0 and 1. And as you go down the screen here, that's time increasing. So the first thing we had to kind of implement optimizations for were spin locks in the kernel. Traditional spin lock, you go to spin on atomic lock word, and you either get it or you sit and spin until it's free, and you can acquire that lock. Well, with micropartitions, when you have two virtual processors, they might not be running at the same time. So it isn't efficient to sit there and spin if the guy who holds the lock that you're waiting to give it up isn't even executing on a CPU. So the first primitive we have in place is a hypervisor call called hconfer. And basically what that does is it puts the thread into a waiting state until the thread being conferred to is dispatched. So if we look here, you can see that we have VP0, thread 0 holds lock A, VP1, thread 1, he's spinning, he wants lock A. He can observe that the guy that has it isn't running, and he'll call hconfer to say, give up my CPU cycles to this other guy so he can finish up whatever he's doing, release the lock, and then I can have it. And then likewise on the other side, we also have a primitive called hprod, which is used to dispatch a thread that's targeted. And some of the implementations of spin locks, what they do is they keep track of, well, I know that VP1 thread 1 wanted this lock while I had it held. I'm done with it now. Since he gave up his cycles, I'm going to take and prod him to wake him up. So here you can see that he's sending a prod over to this guy. He wakes up and he can receive the lock. And then we also have another primitive that we use called hseed, which is basically the way the operating system signals to us to say, hey, I don't have anything useful to do at the current point in time. And you can see here, and let me get the cursor right. So down here where this shows is both threads are seeded. And when both threads are seeded, we can do one of two things. For micropartitions, we can either go over and run a different partition, or for micropartitions and dedicated partitions, that can be a signal to us that we should put the CPU into a power saving state to save power. And then the next time a timer interrupt or external interrupt occurs, we'll return control back to the operating system. A little bit talk about memory here. Like I mentioned before, memory is basically virtualized by taking and splitting physical memory into logical memory blocks. And then each partition has a logical address range that we assign those logical blocks to. The logical range each partition it's not sparse, it's contiguous. Each partition has a memory range that goes from 0 to n. And then we back those logical blocks by physical blocks. So all the references that the OS makes to memory on a hypervisor call, he'll tell us a logical address, and then under the covers, we do the translation over to the physical address. So he doesn't need to be aware of where his memory is really located. To him, it just looks like he has his own memory. And along with that, the OS isn't allowed to actually directly access any of the hardware page tables that are used for translation. So when he wants to insert an entry into a page table, what he'll do is he'll make a hypervisor call to say, insert this translation. He'll pass as a virtual address and a logical address. And then under the covers, we'll make sure that he actually owns that logical address, translate it to the physical address of the memory that's backing it, and then we'll insert an entry into the page table that contains that physical address. And then if he also tries to do things like go read that entry, we do the reverse translation from the physical to logical so that he never sees the physical. And then we also have the capability where when the OS is running with relocation off, he has his own concept of physical address 0. There's hardware support in there where we basically tell the hardware when he's running with relocation off and he accesses address 0 or other low memory, don't really give him address 0. It's offset to another location in memory. And this was kind of nice because it allowed a lot of the operating system code to run unmodified. We didn't have to take and modify the operating system to realize that he has to run with relocation all the time when we moved him over to a hypervisor environment. This is just kind of another picture to drive that point home, where you've got 3 partitions. Each partition has its own page table that's managed by the hypervisor, and all the references within that page table are only allowed to point to memory blocks that are owned by that partition. Talk a little bit about our virtual I/O device support here. Virtual Ethernet was one of the very first things we did. Initially, that was supported with the iSeries hypervisor, and it came over to the POWER Hypervisor when we did that port. And that's basically done by giving them a virtual LAN adapter that looks very much like a physical adapter. It's based on Ethernet, so it sends and receives Ethernet frames. and it has transmit and receive buffers just like a real adapter does. The primary difference being there that when the OS makes a call to send a frame, there's no hardware involved. Basically, would usually be the DMA or sending it out a wire, just becomes a mem copy in the hypervisor. And then internally, what we do is we maintain what's called a virtual 802.11q compliant VLAN switch. So the customer, when they configure a virtual LAN adapter, if anyone's familiar with configuring VLANs on switches, they can go say, this virtual LAN adapter is allowed to access these specific vids on that port. And then the picture here just kind of shows you've got 4 partitions. They're all on VLAN 2 here. And then LPAR 3 and LPAR 4, their VLAN adapters are also allowed to access VLAN 6. But traffic that they were to send out to VLAN 6 wouldn't go over to 1 and 2. And then recently we've also added the ability where the customer can create multiple switches and assign partitions to different switches. And it just kind of provides further isolation from the person configuring it, making a mistake, and allowing 2 partitions to talk to each other when they don't intend that. Something that we added later was virtual SCSI support. This is basically what allows multiple partitions to use the same disk I/O. And what that requires is actually something called a virtual I/O server. The hypervisor itself doesn't have any actual device drivers in it. It doesn't know how to talk to a SCSI adapter or a fiber channel adapter or anything like that. We try to keep that all up in the operating system. So there's a special appliance partition called a virtual I/O server that's based off AIX. And what we do is we assign virtual disk adapters to it, and then we also assign virtual disk adapters to the other partitions that are virtual partitions. And then there's a linkage created between those two when they do the configuration. So here you can see is the virtual disk adapter over in the virtual I/O server, and it's got a link over to a virtual disk adapter in LPAR 4. And we've got 3 pairings here, and you've got a physical disk adapter in the virtual I/O server. He creates volumes on those physical disks and then assigns volumes to each partition. And what a lot of this is used for is customers who don't need the high bandwidth of dedicated I/O. They can basically have one virtual I/O server, one fiber channel adapter, and share that between all their partitions, and it saves them expense on I/O. And it actually uses a standard protocol called the SCSI RDMA SRP protocol for communications between those adapters. I think what we're going to do here is just stop real briefly for Q&A before I turn it over to Greg and have him talk about the I/O subsystem design. So anyone who has questions, raise your hand and we'll call on you. Go ahead. Mm-hmm. You're asking what the performance is, basically? The performance is really variable. It actually depends more on the workload and what the cache effects are than kind of the time slicing. What we do is we actually do partitioning down to 1/100th of a CPU. However, we do enforce that you have to have at least 1/10 of a CPU capacity per virtual processor. So you get down to 10 partitions per physical CPU. What we find there, though, is that if you're switching partitions that often, when you go from partition to A to partition B, by the time you get back to partition A, any cache lines he had in his cache have been cast out. So he basically has to take a bunch of cache misses. But if you only do 2 partitions per processor, you get less of those effects. And that's really has more of an impact on performance than the locking contention issues. Mm-hmm. Correct. Yes, as long as you have enough CPUs to back them. There are customers out there, and we do this for testing all the time, where they maybe only have 2 physical CPUs in the shared processor pool, but they would assign 4 virtual processors to their partition. And in that case, you see a small degradation because you're time slicing more. But if you actually did have 4 processors in the pool, then you would see the same speed increase. Go ahead. Yes. In fact, our hypervisor was really based on a pairing of hardware and firmware from the very start. There's a special execution mode called hypervisor mode and a bunch of other features that have kind of evolved over the years. What we have today, if you look at the full set of hypervisor features in the hardware, it's a lot more advanced than what we started with a decade ago. And we're going to go into depth on some more of that stuff during the workshop that we have after this presentation. Any other questions? Okay, I'm going to turn the floor over to Greg Nordstrom. He works in the I/O area that does I/O support for the I/O hardware, and he's got a lot more experience than I do. So,
thanks, Steve. Just to give a little more by way of introduction, I am an Illinois alum, and since I didn't have an IBM logo shirt, I thought it would be appropriate. I do have an Illinois logo shirt today. I was a student here back through 1981, a computer engineering graduate here. Back at that time, we didn't have anywhere near the facilities you have today, and in fact, we were still programming with punch cards, so that sort of dates me a little bit. We've talked a lot about the processor and memory architecture of the power systems and the hypervisor. You know, processors are always the glamorous, sexy part of the system. Everybody wants to work there, but I/O is kind of that dirty world nobody wants to get close to. But I/O has a big impact on our ability to support these virtualized environments. We do some unique things in I/O virtualization that other computer systems don't do. So as you've probably started to gather, there's a fair bit of complexity in these systems and in the firmware and software stacks that run on top of them. The I/O system is similarly somewhat complex, but we range across computer models. The power systems range from small systems that are one socket, two-way processors all the way up to, is it 64 or 128 way on high end?
64 CPUs, 128 threads.
Okay, 100, yeah, our high-end systems have 32 processor nodes, each of those a four-way node when you include the two threads, so 128-way processor system. And of course, it takes a complex I/O system to feed those processors. So I'll start with, I just have to change speaker notes real quickly, and then I'll get into the I/O subsystem. Okay, so I'll talk a little bit about all of the features here. In our server systems, the smallest systems can be a single, what we call central electronics complex. You may be familiar with that acronym. Sometimes it's just referred to as the system unit. And the reason we distinguish that is because in these servers, we also can attach additional I/O enclosures that are enclosures for additional PCI slots. And that can range from anywhere from up to 6 additional I/O enclosures on the smallest servers up to as many as 92 I/O enclosures on our larger systems. Our I/O in the system is largely PCI. We have pluggable PCI adapters both in the external enclosures and in the system unit. We do sometimes in the lower end servers include what we call built-in I/O, where we actually solder an adapter down on the system planar to save card slots. And then we've also extended our system with the Power 6 line to include some integrated Ethernet built right into an I/O controller on the system motherboard. I'll talk a little bit more about each of these in depth as we go. The external I/O that we attach uses a loop topology, and that's a proprietary architecture that we call high-speed link or remote I/O as it's known among the engineering teams internally. We also use an I/O loop fabric built on InfiniBand technology, which you may be familiar with. That is an industry standard technology, but we use a proprietary tunneling protocol over that to connect the PCI controllers. As Dave described earlier, in addition to processors and memory, each of these I/O slots can be individually assigned to partitions. I'll talk a little bit more about that later in the slides. But we partition down to a physical adapter. Some of the other virtualized systems in the marketplace actually partition at physical boundaries of an I/O drawer or a system enclosure and don't actually partition down to individual adapters. In a system, on our largest systems, for example, we can have upwards of 1,000 I/O adapters in the system. Any one of those adapters in any location in the system could be assigned to any partition. And we should also mention, even though we virtualize these systems heavily and we can partition to very large degrees, any single operating system can also, we can configure the system as a single operating system server, and the operating system by default owns all of the resources of the computer. I did mention a little bit about modularity earlier on. We have two design points in our model range. We have what we call our Model 570, which has 4 processor nodes, like in the blue box at the top. So we would have 4 nodes that look like that structure and can attach external I/O enclosures. And then our high-end systems are processor memory nodes only and attach lots of external I/O with these green fabric controller bridges, and we can have up to 32 of those. Within the lower-end systems in particular, we have I/O controllers that provide internal PCI host bridges. We have built-in I/O like PCI, SCSI, or SAS and USB devices built into the low-end servers. And this just kind of gives the customer an integrated package all in a small server. The I/O controllers are an ASIC that we do as proprietary chips. They're very similar to chips you might see from companies like Broadcom or NVIDIA that have integrated host bridges and integrated adapters. And in those KEC systems, we provide both pluggable and built-in slots. So each of our lowest-end systems provides at least 4 or 5 pluggable PCI slots. Generally, those are hot pluggable, except in the smaller 1U and 2U boxes where the packaging just doesn't allow hot plug capabilities. I'm going to move a little quicker through some of these. In the larger systems, as I mentioned, we provide an escape to external I/O so that we can get sufficient additional slots to feed all those processors in memory. Each of these I/O external enclosures connects through a fabric controller, and as I mentioned, we have a proprietary fabric we call high-speed link, and we also have InfiniBand fabrics. And our InfiniBand fabric controllers can be modally configured as either I/O loops like this, or to use the standard InfiniBand clustering, which is called the host controller architecture or host channel architecture. That's used for high-performance computing clusters. And so we, in the hypervisor firmware, can configure those controllers in either of those modes, but we can't support both modes simultaneously because the tunneling protocol really doesn't support simultaneous multiplexing of both HCA protocol and tunneling protocol. And within a loop topology, we connect anywhere from a single up to 6 drawers in one loop. Drawers are rack-mounted form factors. We also have standalone towers, which look like small racks of their own. And in addition to the in-band control that the hypervisor performs through these HSL and InfiniBand links, we have an out-of-band service processor connection to power on the drawers, sequence that powering on, and to enable independent power control of each enclosure. Let's see if there's... we have an architectural maximum of 32 controller hubs and up to 16 drawers per hub, but in practice we actually support a smaller number of these. We limit the loops to 6, and we limit the total number across the system to on the order of 92. And that's really just a testing statement. To build these systems and test requires a fairly high capital expense investment. This is a multi-million-dollar machine by the time you get to nodes that large. So we limit that from a testing perspective, but also, we try to tailor that to what the customer demands are. So as customers kind of indicate a need for greater, then we certainly look at doing that. One thing that this architecture does for us is it allows us to do fairly dynamic configuration and repair of segments of the system. We can power off an individual I/O enclosure. We can repair that enclosure. We can dynamically add new enclosures. So you can open a loop, insert a new drawer, close the loop, and do all of that without disruption to the operating systems running to those other adapters. From a partitioning point of view, all of the hardware that makes up the I/O system above the physical PCI adapters are what we consider platform hardware and are managed by the hypervisor. So when you boot the system, the hypervisor configures those adapters, or configures the bridges that create those connections to the adapter slots, but does not directly configure the adapters themselves. Those are presented to the operating systems as if there were no hypervisor present at all. The operating systems and device drivers control those adapters directly as they would on any system. So a Linux device driver, for example, that runs in x86 Linux works with a power subsystem with adapters it recognizes with no direct changes for the device driver itself. We, in hypervisor, recognize all the adapter slots that are detectable in the system at boot time or when they're dynamically added through a concurrent add of a new enclosure. And we keep those as a pool of available resources. System management tools let the customer then individually assign adapter slots to partitions. And just like we do with processors and memory, we can dynamically move adapters between partitions as they're running. A typical case for doing that sort of thing is if, let's say, LPAR 1 has a tape drive that uses once a day. LPAR 2 also has to do a tape backup once a day. But neither of those partitions need to have access to that tape all day long. So a customer, rather than buying 2 tape drives, can simply move those tape adapters between partitions dynamically as a need is there for each of those partitions. One of the key things to enable this kind of partitioning, though, is the adapter isolation. And this is where we put a lot of our effort in the hypervisor. We do also, as we do with processors, we have unique PCI host bridge architecture in our host bridges to enable additional isolation. Critical here is error domain isolation. The obvious things are isolation of address spaces. One adapter can't ever be permitted to DMA to memory in another partition. A device driver running in one partition can't ever be permitted to access the PCI memory space that maps facilities in another adapter that it doesn't control. But error domain is one of those sort of afterthoughts, but it's really kind of key to enabling partitions to run and tolerate the loss of an adapter somewhere else in the system. And as Dave mentioned earlier on, if a physical adapter fails, we don't allow it to fail in such a way that it can disrupt operations on other adapters that might be sharing either the PCI host bridge or fabric bridges and hubs in the system higher up. If you're familiar with the more typical model of I/O, typically when a device takes an exception, particularly if it's an exception that affects DMAs, it's often reflected as a machine check backup to the processor. At minimum, it's a full loss of that adapter, but more often it actually takes down a whole system. And we do a very good job of isolating with this proprietary hardware so that never happens. Physical adapters can cause loss of a single operating system if the operating system itself isn't robustly designed, but they'll never cause loss of an entire node or fabric path to other adapters sharing that path. If you do go and look at the PAPR architecture under power.org, you'll see an architecture description there called Enhanced Error Handling, or EEH, and that's the key to this. The device drivers can recognize an error state, and we build hardware support around that error and extended error handling architecture to build fencing points in the hardware. So at each of these points, we can fence not only individual adapters at their PCI connection points, but should we have a hardware error, for example, in a fabric bridge, we can fence that fabric bridge in such a way that only the domain surrounding that fabric bridge is affected, only those partitions using resources below that bridge are affected, and all of the other I/O in the system continues to run. And EEH is, even though that's really more a device driver specific architecture, it's kind of key to making that happen. It is an architecture that I think only the PAPR compliant operating systems support. I don't think there is an equivalent in other operating system environments. And we do unique Linux development to support EEH as well. One thing we've added with the POWER 6 is an integrated Ethernet capability, and this is built into one of our PCI I/O controllers. By integrated Ethernet, we have between 2 and 4 physical Ethernet ports that can connect to this I/O controller, and the customer can configure that by buying different port cards that plug in below this. But then we can materialize up to 32 logical ports over that, and one of the advantages of this is that those logical ports then become partitionable resources, and they're just there out of the box. As good as virtual I/O is, the one complication of virtual I/O is the customer has to create a VIOS server partition. He has to administer that partition. And with integrated Ethernet here, these logical ports are just there when the box boots. The customer can assign the entire set of 32 logical ports and reconfigure that as a smaller number of logical ports across those physical ports to just one partition, or he can just simply assign those 32 ports to individual partitions. And we're finding very favorable response in the marketplace because it just lowers the customer's administrative effort to simply assign these resources rather than have to manage an additional partition. In the 570 model, that particular node design includes one of these I/O controllers in each of the nodes, and so when you have 4 nodes configured into a 16-way system, you can actually have a total of 128 of these logical ports. So you can actually support quite a significant amount of partitioning with very limited administrative effort. So as you know, just kind of to summarize some of these features, we partition our I/O subsystem at the physical adapter. As I mentioned before, any adapter anywhere in the system can be assigned to a partition. It's up to the customer to decide how to administer that. I should also mention that any adapter in the system can also be configured under a virtual I/O server. So literally you could multiply all of the physical adapters you have by the capability of partitioning those individual adapters into virtual I/O volumes or network ports, and really multiply to a very large scale the number of physical or of virtual resources in I/O in the system. On our larger systems, when we get up to that 92 number of towers, that really results in on the order of about 1,300 PCI slots. And if you sub-partitioned each of those, you could imagine you can get to very, very large numbers of I/O resources. The EEH architecture I mentioned, gives us the ability to do this very advanced error handling. We can continue to keep partitions alive, keep the computer alive, the servers alive through errors in multiple points in the I/O infrastructure. One of the things Dave didn't mention, but it's very common for our customers, particularly our high-end customers, is these customers expect one outage annually that they schedule of the entire system. Typically when they schedule outages, that may be like a 4-hour service window. So these systems are running literally 7 by 24 by 365, and customers expect that kind of availability is there built into the box. So these error recovery facilities and logical partitioning capabilities are very key to doing that. And when Dave talks about partition mobility in the workshop, that's another aspect of providing that kind of availability, because partition mobility will allow us to actually move partitions between independent servers, so that literally a customer could configure 2 adjacent servers, and if one server needs a service window, they simply move their partitions over to another server, continue executing. Those partitions never get shut down, and you can effectively get continuous availability of all of your infrastructure. Concurrent maintenance is another advanced feature we have here. In addition to PCI hot plug, we have these I/O drawer hot plug and concurrent or dynamic add, dynamic repair. We can power off if you were to have a hardware failure in an I/O planar and an external enclosure. We can power off that enclosure, repair the planar, and then power on that enclosure. And we use our dynamic LPAR capabilities, the ability to move adapters in and out of a partition as part of that concurrent maintenance. So virtualization, again, plays into the ability to do this. We can take a drawer that needs service. We can communicate with those operating systems that are using resources there through our hardware management console, say, we're going to remove these resources from your operating system, pull those out, go service a drawer. When that service is done, we just use a dynamic LPAR add to bring those resources back into the partition. So I think, we're into all the trademarks now. So I think I'll stop here. Is there any questions you have at this point? Yeah, I/O kind of loses its glamour, I know. Oh, there's a question. Ah.
So normally with operating systems, you can optimize inter-process communication using names like shared memory. Is there any thought of that in the I/O systems design so that I've got one processor that's saying doing network communication with another processor? Any way of optimizing that?
We do have the notion of what we call I/O pools. They're not really a dynamic sharing, though. I mean, today, no. We other than virtual I/O VLAN connections between partitions, which can be a little more optimized, so you don't have to move data twice between the same I/O device. Generally, no. We don't have the capability today to map multiple partitions to the same. Or multiple adapters, for example, to different partitions memories concurrently.
Yeah, for the most part, we've tried to avoid sharing memory, but we do have a lot of people that are trying to push us there for performance reasons. The one thing we do have is something called remote DMA, though. So the example I had where you have the virtual I/O server serving out disk requests and virtualizing a physical disk, it actually is allowed to directly map the other partition's memory in the DMA table so that there's no copy involved in the middle there. So it basically just takes a request from the client partition, sends it down to the adapter, and the adapter DMAs that storage directly into the partition's memory, so there's no copy in the middle there. That's pretty much the only place we have where we've done the sort of storage sharing like that today, though.
No, no. What it means is really it's just a system administrative action. So the customer goes to a hardware management console, says, okay, I want to move, identifies a particular resource like a PCI adapter, to use my earlier example, tape drive adapter, and partition A may own that or be assigned that adapter at that point in time. The customer says, well, I want to remove it from partition A and I'm going to move it over here to partition B. He does that through the hardware management console. That does trigger some communication between the HMC and the partition to say release control of this resource. There's an architected flow the partition performs to say, okay, I'm going to release this. Once that's released, the hypervisor actually, as part of that flow to dynamically remove ownership of that partition, we take actions to the adapter itself. We don't do anything to the rest of the partition. And so, for example, as I think Dave mentioned earlier, we do, where we have hot plug power control to adapter slots, we'll actually power cycle the adapter. So it has the effect of an air-separated computer transfer, between two air-separated computers. If you were to remove an adapter from one computer and plug it into another, we want to have that same effect. So a power cycle would have that effect to the adapter, flushing any transient buffers that might have partition A's secure data. Obviously, if you have non-volatile memories, then you have to have device driver support to clear out partition A's non-volatile information. But typically, adapters would have buffers that might have residual data from transactions there that if you didn't power cycle that adapter, and if you're familiar with PCI, the reset architecture in PCI is a little on the weak side. So you can't rely on something like just a simple PCI reset to clear those transient buffers of data. And what that would do is then when the partition B took control of that adapter, if we didn't flush that with a power cycle, it would be possible that when that next device driver remaps internal memory in the adapter, he might have memory mapped access then to residual data that was private data. So that's one of the reason we do that, but that's about the only action that occurs to the hardware under the covers, and that's totally transparent to the operating systems and the customer. Another aspect of that power cycling too is when partition B takes over. Typically the device drivers are written such that they expect an adapter in a very specific state when they initialize the adapter, and so you don't want to have an adapter in some kind of indeterminate state that the device driver now may not be able to configure that adapter because it's just simply not robust enough to recover from some arbitrary state. So that's another aspect of that. We do have some cases where we don't have hot plug power control because, particularly in small boxes, hot plug power control. Is this a general computer engineering audience or mostly software? You know, if you have some electrical engineering or computer engineering background, you know, providing hot plug controls to individual adapter slots usually means providing not only power FETs to control those slots, but also multiple power and ground planes to isolate those slots relative to the rest of the power on the planar. And so that becomes kind of a high expense. And in small systems, that tends to be more expensive than we want to build in our base packaging. So for those slots, we still do rely on at least PCI resets. But you know, at that point, you have to rely on the device drivers, and we identify to our customers that, you know, those slots aren't as secure and dynamically moving between partitions. Have I answered your question, though, as far as you know how logically this occurs? Okay. That's true also of these integrated Ethernet ports, the logical ports. Those can be moved, you know, with really a system administrative action. Being this is largely a student audience, you know, that's one area that is kind of under vigorous development now is system management. Yeah, I mentioned we have 1,200 to 1,300 physical resources, physical adapters. You can imagine as a system administrator dealing with the complexity of managing that many physical resources assignable to even a small number of partitions. As we carve those up into virtual resources within an adapter, and there is emerging technologies within PCI to sub-partition adapters that we'll be leveraging in addition to our own virtual I/O server capabilities. You know, the complexity of the number of resources is really quickly scaling up, and the system management tools have not really kept pace with that. So as programmers, you know, this is an area of pretty vigorous invention and innovation. So, you know, that's one thing I would recommend to you is if you're interested in virtualization, that's an area of virtualization that still has a lot of room for innovation, and an area you might, you know, think about as you're trying to refine your interests. Any other questions? The principal difference with virtual I/O servers is that you have some additional mapping overhead. So if you're remapping buffers frequently, you're going to notice a little performance degradation because you have to communicate with your VIOS management partition and the hypervisor to do that mapping. Where a device driver running to a dedicated physical adapter simply has to map its DMA buffers directly through the hypervisor. I don't know, Dave, is there anything you'd add?
I guess I can kind of add to that. What we find is that a lot of customers, if they really care about performance, they do go use the dedicated hardware adapters. However, there's a wide range of customers that they don't care as much about performance as they care about the flexibility of their configurations. And those are really the customers that go for the virtual I/O server and do the virtual LAN and stuff. And there's a lot of other things like you have to use the virtual I/O server to enable partition mobility. So if they want those advanced features, that kind of drives them in that area.
It kind of raises another point about virtualization of I/O. You know, one of the trends we're seeing is that, and this is not unique to Power or IBM, but as you look at physical computers, the number of processor cores and the amount of memory in proportion to the number of physical I/O slots, the processor and memory capacity is increasing much faster than the number of physical I/O slots. So virtualization of adapters is becoming increasingly important simply to get sufficient I/O capacity per processor core or thread. I mentioned an emerging standard, and in particular that standard is in PCI single root I/O virtualization. That standard actually was just published, I think, a month ago publicly, their version 1.0 standard. And what single root I/O virtualization does is it allows an individual adapter, it provides the PCI standard architecture to sub-partition an adapter into very, very many virtual PCI functions. And they can be mixed functions, like today some PCI adapters will have Ethernet and maybe USB on the single adapter. The single root I/O virtualization standard will allow you to do a similar thing. You can have multiple images of a particular adapter or device class and have mixed device classes, but that's becoming very important, particularly in the smaller form factors like PCs or single unit, 2U, 4U size unit processors, where the I/O slots are very much in competition with physical real estate in the rest of the package. And so, vendors tend to skimp on I/O slots in order to get memory and processor capacity. And so that really puts a lot of emphasis here. And so, I/O virtualization is another area, within the industry that's really got a lot of opportunity for programmers and computer engineers. It's really, the rest of the industry is really starting to just come to this level of I/O virtualization now. Any other questions? We've got a few more minutes if you have some. I'm not usually known for keeping presentations on track. So for me to be ahead is unusual. Well, I guess in the next hour, we'll be talking a little deeper dive. We're going to spend a little time on some of the development principles behind the hypervisor, a little bit on the metrics of the hypervisor as a large project, and then Dave is going to spend a fairly in-depth discussion on partition mobility, which is something we've mentioned a couple times, the ability to move partitions between running servers. So if you want to join us for the 11:15 session, or is it 11:15 or 11:30 when that starts? Okay, 11:30. It's in the, I'm not sure which room we're in, but 11:15 in what, 1304? So if you that workshop is undersold at the moment, so there is some available seating capacity if you want to join us for this, and we can also entertain more questions on the hypervisor architecture, Power 6 architecture, if you're interested during that session as well. So thank you. Looks like most everybody managed to stay awake for an early Saturday morning for students. I'm sure that's a challenge.